from the middle of China. My university's name is Huazhou, means Central China Agricultural University. One of the 4 agricultural universities supposed by the national government. So today I get a chance to present what we did for citrus research. From 1980s, we began the biotechnology merged together with the classical breeding to improve our citrus variety. So I just give skip the introduction. Firstly, the general information of citrus. Citrus is the number 2 fruit in my country, constitute about 21% of the total production. The production increased very quickly during the past 10 years. Also, right now it's number 1 producer of citrus. If we look at this picture, you can see the biggest one is about 2,000 grams, and the small one just 1 gram. But most of the citrus in this area is big one, about 200 grams for each fruit. So this is a truly picture of the size of different fruit. And there are many types of citrus. For example, this one, the biggest one in the left, pomelo, and the small one is the white citrus in the mountain. As you know, most of the citrus originate from China, especially for the cultivated citrus, the tangerine, mandarin, and the sweet orange. Yeah, this is very common name orange. Yeah, in Spain, United States, and also in China. And this the mandarin in my area is the most popular citrus, but it mature just in October, in October to December. Yeah. The other type for ornamental, and also this one citron for ornamental. So I just give a brief the picture of our citrus. What's our problem? What's our target? So there are many problems when I was a student, but after 1980, after I got the position in the university, so I focused on the seed problem. At this time, most of the citrus is seed. Many seeds. The most, the one variety can sometimes more than 100 seeds. It's easy, or it's not easy to eat. So. At that time, we began to try to solve the problem. Of course, there are many pathways. One is the genetic improvement. Another one is to explore the germplasm. You can find the bud spot like in the Satsuma mandarin, and also you can find the bud spot like navel orange from common origin about 200 years ago. So this is our strategy, our pathway. Firstly, we try to go to the tetraploid by prototype fusion. And then we hybridize with the diploid, and then got the embryo skill to get triploid. This is our pipeline or pathway at this time. So in 1987, when I was a PhD student, I set up the protoplast degeneration system. And 2 years later, we get the system for protoplast fusion. This means we can get oral tetraploid. So this is the first step, get tetraploid. Of course, today we have a bunch of the tetraploid of citrus. So we got about more than 40 oral tetraploid for citrus. Some is intergeneric, and most of them is specific. But today, more and more, the oral tetraploid was was generated by this muscle in the United States and also in China and other countries. So after we got the tetraploid, we hybridized with the diploid, and then we got the embryo skill. As you know, most of the citrus is partly embryonic. If you just get the fruit get mature, most of the seeds you can get germination, but you just got the palm, the genetically the same as the mother parent. So got the embryo scale and the chromosome, and then got triploid. So this we got triploid, and they transplanted the field, and of course we test with the worker mark. Is a true triploid or is true hybrid, or in case the chastity. And then years later, we got the plant, get the flower, the set of fruit, and of course is seedless. So this means this way is successful. But if you say the timetable or the time list, we spend about 20 years to go triploid, very, very long, and generally 2 generations for get this. Of course, recently we get more triploid, get the fruit and the shoe is seedless, of course. And but recently we tried our strategy. We got the triploid. Generally, they are very long strong, and the tree is very vigorous. So we try to transfer the cytoplasm of Satsuma mandibuli. Satsuma mandibuli is CMS. This no pollen if the normal condition, and they can sell food and no seeds, so seedless. So we try to just transfer the CMS from the seedless variety to the seed variety, but we don't change the nuclear. So firstly we got the fusion, and then we got the regeneration. Then we select the diploid, and then we use molecular mark to select the diploid with the cytoplasm of Satsuma mandibuli. They just change the cytoplasm. And then this is a case, successful case. The left picture is the Satsuma mandibuli seedlings. The right picture is a variety we call HB Pomelo, is CD. After we fuse the protoplasm and get the degeneration, years later, they degenerate flower. You can say the upline is the pomelo, the bottom line is the cypress, the fusion degenerate. So the answer is degenerate, no answer. And then we can say the fruit is seedless. So this way we can improve the CD tree just on the level of diploid. We don't worry about the increased chromosome number. Yeah. So this is the typical picture. The left side is the cypress, and the right side is originally the pomelo. If you see the tree by the naked eye, you cannot identify who is who. So this means most of the variety, or most of the trait of the variety is the same. They just change one trait, CD, from CD to seedless. So the left column just tell you how much time we spend about this. From 1987, we got the protoplasm platform, and 2010 we got the cypress, the seedless variety. And just last year, this variety is got a patent and protected by the UCOF system. Of course, we use the tissue culture system or the biotechnology system to generate more germplasm, the auto-tetraploid, and also we use this technology to try to, we call it separate the chimera or the chimera cell, and we just get this kind of cell to try to regenerate the plant, and we got tetraploid very easily if the peel is become very sick. So this got tetraploid very easily if you just isolate this section in the medium. Recently, we tried to initiate the DH line, this means a double haploid for our genome sequencing. So in 1980s, we have this protocol, but recently we use this protocol to get the degeneration of the sweet origin for the DH line. In 2010, we got this DH line, and then we promote this work for our genome sequence of sweet origin. 2011, we finished the sequence of sweet origin, and then we publish this, and also we have a website. Anyone can use this platform for the seeds of sweet orange. And during this research, we found the sweet orange come from the cross of the pomelo with mandarin, and then hybridized with mandarin again, and then we got the story of the origin of sweet orange. Okay, I would like just to shift to another very quickly to other picture what we did about the germplasm for the evaluation with the molecular mark. We have a lot of germplasm in China, and sometimes they give the name actually the same variety. So we use this molecular mark to identify who's who. So we developed a lot of the kind of the molecular mark from SSR to SMP today, and to try to identify the variety. So just to show you the cytoplasm mark for actually it's chloroplast mark for identify the cytoplasm for each variety. And also we try to explore a variety from the naturally open field to try to also get seedless. This was original CD, but right now we got seedless gene changes and a variety locally for orange juice and also for table. And another one is the later mature variety of navel orange, like Lindley or Levelate as is Spain, but this one is in our area. Okay, this is another Camaro variety of the sweet orange with Sazuma mandarin. Well, first we use the molecular marker to identify who's who and the structure of peel and also fresh. So I won't have the time to explain slice by slice, just to show you. We use the molecular marker to help us to identify the variety and identify the bud spore. Yeah. And after we got this bud spore, it's truly the new variety, we can release to the industry and they enlarge the number and got the benefit for the farm. This is typically the Chinese 6 orchard. It's not like here. It's very plain, but it's a hilly area, mountain area. Yeah. Finally, I would like to say, after we got the new germplasm or with the germplasm with the allied tree, we can research on special traits. For example, this picture shows you different color of citrus. We have different, many variety, but the color is different. So during the past 10 years, we got a bunch of the mutant. But this set of mutant, just one pomelo, but the different color of the flesh and also the peel. The other side, the picture show you a mutant. They accumulate the lycopene from the common sweet orange, and the bottom one is the pomelo. They accumulate also lycopene and also beta carotene. They give the strain. So in the past year, we try to understand why they accumulate this kind of special pigment. And I have no time to explain one by one, but I show you. Given the variety, they have given the promoter for this PSY gene. So if change one promoter, and then they will change the content of the carotenoid, and then change the color, of course. Yes, I'm not showing you detail. Last slide I will show you. For the annual crop, it's easy to get the hybrid and get a population for genetic research or for the genomic research. But for per-annual crop, for citrus, also apple or other trees, very difficult. So during the past year, we dreamed we can find a model plant like the arabidopsis or like a cotton or like the rapeseed. 1 year you can get a seed from seed. So during the past 10 years, we tried to find the germplasm of White Mountains area. For 8 years, we got one assertion. This assertion, you can see, after we seeded we saw the seeds, and then we get the fruit in just 1 year, in about 6 months. And then we can go to this 1 year cycle to research on the genetic and genomics. of course, it should be mono embroidery. Originally, they have this, we have this kind of gem plant, but it's polyembroidery. So you're very difficult to get hybrids, okay? We call the that get the truly hybrid. But right now we have this system, and we try to put the transgenic system for this the special assertion, and then also we try to verify this is reliable. So we transfer the PSY gene to this assertion, and we can check the color of the fruit and also the flower. And recently we use this system to try to understanding what is specially tree in citrus, polyembroidery. So why is one seed have more than one embryo? The most one have 48 embryos. So if we can understand the mechanism, maybe we can use this gene for other crop. For example, for maize, for rice, we can keep we call the heterosis by this strategy. So during the last 3 years, we got a big population of this small mother plant, and the ones just 200 square meter, we keep about more than 1,000 plants, and then we can get the fruit. And in just 1 year, you can get the fruit from the seed to the next generation. So recently, we localize this kind of the gene chromosome number 4 and a very strict area. I hope in the future we can got this the tree to localize and got the key gene control the polyembryonal tree. Okay, I just skip my research. So I summarize that during the past 30 years. We integrate the cell fusion, tissue culture, and the conventional breeding channel together to generate the triplet and the cyclic to improve our the CD trait of our citrus variety in China. Secondly, we construct the platform for citrus genetic improvement, including the whole genome sequencing of sweet orange and the exploitation of seed to seed with annual like a model plant for citrus. We hope in the next future we can share this model system and also the platform for our international community. Thank you.